Hello everyone, and we'll pass to the next presentation. And I'm very happy to present you today. Romain Moral, who joined the onboard data handling department of CNES, so the French space agency, as well as Bruno Saba, who is also working in this onboard data handling department of CNES, and who is as well a member of the space data link security, so from the CCSDS committee. So welcome to the stage. The floor is yours.
Thank you.
Thank you, Anna. Good afternoon, ladies and gentlemen. With my colleague Romain, we will try to present you the Cryptoserver, low-cost Cryptoserver for the new space market. We'll see the needs, then the main features, what's inside, the integration in the control center, complete system, crypto system overview, and we will finish by short demonstrations and questions. First, the need. Why do we need a crypto server, a hardware crypto server? We need to protect the links, the communication links between the space, the satellite, and the ground, the control center. The uplink first, the telecommand link. We need essentially authentication. We need to be sure that the command comes from the control center and not from an attacker. For the downlink, the telemetry, the main feature is confidentiality. We do not want the data coming from the satellite to be used illegally by an attacker. How can we protect the communication links? We will use symmetric cryptography. I will define that later. Because we will use very well-known and proven algorithms which are standardized, which are efficient, and resistant to quantum computer. We will use also protocols. The first one is the SDLS, Space Data Link Security Protocol, which has been standardized by the CCSDS. And it can protect the TC-Link, uplink, TM, and AOS, which is a downlink for payload. Everything related to security will be applied to the TC, or the CCSDS transfer frame. So now, what does symmetric cryptography means? There is a secret parameter which is called a key, which must be known from both ends of the link. The key will be used at the sending end to protect the data, and the key will be used at the receiving end to use the data. The key is a secret, and it must stay a secret. Everything else is public. The algorithm, crypto algorithm, standards, like SDLS, everything is public. This is a Kerckhoff principle. Everything can be public, but the keys must not be public, they are secrets. If the key is compromised, no more security. That's finished. So now, how can I protect the keys from compromission? Let's see on board. On board, it's quite simple, because the keys will be buried deeply in the onboard crypto unit. They will be injected before launch. There is no big leakage threat analyzed if the crypto unit is designed correctly. Now, on ground. On ground, we need the key in the control center. In a control center, everything now is done in software. So the keys will be somewhere on a server in the control center, or even in the cloud. Why not? No. This is simply not acceptable for some missions. That was the start of the design of the crypto server. One customer told us, no, I do not want my keys to be inside a server in a control center. So why? First, key compromission doesn't leave any trace. It's easy to copy a file to another one. Nobody will know. When you realize that the key has been compromised, it's too late. The attacker will have gained control of the satellite. Can someone here say, nobody will access my key in the server? Can one of you say that? And be sure. And say, I will be killed if someone does. I've listed some features, some possible compromission issues. Large attack surface of the server, vulnerability in the operating system, compromission of root password, etc., etc. Even a crash, a system crash, where you have a core dump. What will you do with that? Send the core dump for debug to the manufacturer? Can anyone be sure that there is no key inside? No, impossible. So now what do we need? We need a physical vault, a physical safe for the keys. Any access to the keys from the outside must be impossible, which means that every crypto calculation, crypto computation must be done inside the vault. It must not be shared with anything else, dedicated crypto module. And it must be simple to use and to interface with the control center. Why? Because if it's too complicated, nobody will want it. And the last one, it must be low cost, because we are targeting the new space market. And the solution is the low-cost crypto server. So let's see the main features. We will need one crypto server per link, 140C, at least one, 140C, 140M, one for AOS if it is used. It must be, of course, CCSDS compliant and SDLS compliant. For the crypto algorithm, we will use AES 256 bit length key, GCM as an operation mode for authenticated encryption, and CMAC for authentication. It will have to manage the IV internally. The interface with the control center will be as simple as possible using Ethernet TCP/IP. And the performances, 50 megabits seconds in deciphering, or 10 megabits second for the TC link, for protecting the TC link. We need to protect the key, so let's say a word about the key storage. We will have one master key, key encryption key, which will be stored in red, in clear, inside the microcontroller memory. It will be buried in the microcontroller so that nobody will be able to extract it from the chip. And the traffic keys, the keys used for encrypting the traffic, will be stored, ciphered in an external memory, which means that no red key will be available outside the chip, outside the microcontroller. The key distribution now. If we want to change keys, we will simply have to deliver the new key ciphered to the crypto box, to the crypto server. It will store it in its memory, and when the need to use it arises, it will decipher it with the key E-key. For the security, we target a common criteria EAL3 plus security evaluation. This is not done yet. It is in an ongoing process. And we use no operating system. Everything is bare metal, so the attack surface, which is linked normally to an operating system, is removed. Let's see what's inside the crypto server. Here you have two views, the front view and the rear view. You can see some LED push buttons, and the rear panel, one TCP/IP, one Ethernet connector, and the power supply connector. What's inside the box? First, the box in itself, made of two parts, two halves in aluminum, with one fixing tab, which is here, which allows the box to be tied to its support to avoid someone taking it, removing it. We will also apply some security stickers on the screws. And inside you have the PCB with everything electronics, the microcontrollers, the memory, Ethernet fee, etc., etc. And you need an external 5 volts to power the crypto server. If we look at the architecture, it's quite simple. You have one microcontroller, the external memory for the ciphered keys, power supply distribution, Ethernet access, and control, LED push button, etc. So the A key will be stored inside the microcontroller, and the traffic keys will be stored unciphered here. So they will be read, deciphered, and used inside the microcontroller. If we look now at the integration in the control center, as the name implies, the crypto server is a server. It will listen on one predefined port, TCP/IP port, and it's up to the client to open the connection. Only one connection accepted at a time. It works at CCSDS transfer frame level, one frame in, one frame out. We need a simple protocol to signal the errors that can arise. So one single byte will be added at the front of the frame. So if we look at the direction from client to the crypto server, from the control center to the crypto server, the first byte will indicate the action to be done by the crypto server. Cipher the frame, give me the list of keys you have in the box, etc., etc. On the other side, from the crypto server to the control center, this is a reply, and the first byte indicates the result of the requested action. If it's 0, then everything is okay. If it's different from 0, then there is an error. This is a CCSDS transfer frame. And what we did is simply add an opcode. So the protocol is quite simple. Open a TCP/IP connection, add the opcode, send the frame, you will receive the frame with the error code and use it. Some examples of opcodes and error codes. If this is 0, for example, it can be cipher the frame. If it is 8, it's give me the context, how many active essays, associated key IDs, associated IV or IRSN values, etc., etc. If we look at the error codes, 0 is no error. 41 means no active essay for the requested frame, etc., etc. Error codes are hierarchized. The first level is just information. Normally, the frame is processed correctly. You can have some level 2, which is minor error. For example, if there is no active essay associated with the requested SP, if I do not have a key, I receive a frame to cipher from the crypto server point of view, and I do not have a key to do that. So the crypto server will reply with an error code, a minor error, and the frame data will contain only FF, so that it cannot be used. It has not been ciphered correctly. A major error would be, for example, an unknown opcode. If the crypto server receives an unknown opcode, it can mean that everything is desynchronized. So in that case, this is a major error. The crypto server will close the TCP/IP connection, resets all its internal buffers, and wait for a new connection. And it's up to the client to start a new connection. This ensures that we have everything resynchronized correctly. If we have a look at the complete ecosystem, on the ground, we need a crypto server. We also have a key generator, key management system, a test bench, and simulators need to pre-integrate the system. On board, I will not go into deep details. We have a full software implementation, a mixed hardware software solution if needed, and a full hardware version which is under development. What is available? The crypto server will be at the end of the year. A key generator, key management system, everything will be available at the end of the year. The price now, around 1,000 euro. Yes, around 1,000 euro. Okay, this is low-cost crypto server. On board, I will pass that. I'll give the floor to my colleague Romain for the demonstration.
Thank you, Bruno, for this clear explanation. For the next 5 minutes, my mission is to try to show you how easy it is to use the crypto server. So, as Bruno said, the crypto server can perform different tasks, cipher telecommand, decipher telemetry, AOS telemetry, and we can use it to do random bytes. So in this case, I will try to decipher AOS telemetry. So at first, in this box, there is just the bootloader. There is still no application. So I have to upload the firmware that can perform the AOS deciphering. So I will connect to the crypto server and upload the binary. So for security and confidentiality, the binary is signed and ciphered. So I have previously uploaded a symmetric key and the public key to check the firmware signature. So now the firmware is uploaded. So now if we can check, you can see, but the blink LED indicates that the firmware is well uploaded. I have to upload the key, as Bruno explained earlier, to decipher the traffic key. In this case, the public key, the master key is also wrapped and signed for security reason. So this is the key. So the crypto server checks the signature and uncipher the key and store this key in this flash. And now I have to upload the traffic keys. So I have already wrapped the traffic key with the master key. So there is one key injected. And now I can check that I can ask the crypto server the context to know if this key has been installed, and this is the case. It indicates the index 1 and the SPI 5, 6, 7, 8 in this case. And now I can go to operational mode, which is the normal mode in the control center, to decipher the telemetry. I will show you for the people who loves hexadecimal representation and well-known the CCS, the SDLS protocol. You can recognize a TM frame. You can see the IV here and the SPI 5, 6, 7, 8 we showed in the previous HK hashcat tool. So I added the opcode to indicate to the crypto server that you have to decipher all this file. So now I connect to the crypto server. I send, so we can see here the bitrate. It's close to 55, 56 megabits per second full duplex. So we have received the same data length that sended, and we can check now that the error code is 0, and we can see that all the frame are deciphered. So this is the end of this small demonstration. So if you have any question, we can answer, and you can come to the CNES booth to discuss about the crypto server.
Yeah, thanks for the nice presentation. Looks like a really interesting box. I'd be interested in knowing if there's, do you have also applied any link security for between the crypto server and the operation control software, or does it need to be a point-to-point connection? So do you have TLS deployed on there, or is it just a plain TCP/IP connection?
It's just a simple TCP/IP. There is no security between the crypto server itself and the control center.
Okay.
The crypto server must be in the control center. It cannot be remote.
There is a feature. The control center can challenge the crypto server with a challenge. The control center send the random data. The crypto server will sign this random data, and we can check the signature with the crypto server public key. So we can be sure that we are talking to the right device.
Okay. And the second small question, just for understanding. So I basically prepare my, if I want to do it for upload and for encryption through this crypto server, I prepare my TC frame with space.length security protocol headers already in there, just plain data and empty fields for the security tag, and this is what the crypto server then will apply. And
yes, you have to prepare the data to the crypto server for the Mac, and the crypto server will overwrite this data with the Mac computed.
Okay, thanks.
I have two questions. First, do you have a key injection mechanism to inject keys into the flight system?
We have for the crypto server, we have a key injection mechanism. It has been shown rapidly. The first one is to inject the key key, which is done securely because there is an asymmetric mechanism. But you have to build the root of trust at one time by putting the crypto server near the injection PC. Then the traffic keys can be distributed by the network because they are ciphered, so there is no problem. You can exchange the traffic keys by email, no problem. The algorithm uses this key W, which is normalized by the NIST, with underlying cipher box is the AES 256.
Okay, the second question, do you handle also all the life management of the keys?
The life management of the keys, this is part of the project management. This is not at the crypto server level. When you need to change the key, the crypto period, etc., this is defined by the project. When they need to change key, just send a new key to the crypto server and use it. You can have many keys in the crypto server. So you can still use the old one, and when you decide to use the new one, just send the frame with the new SPI, and that's enough.
We can also kill key inside the box too, securely.
Any other question?
Just to understand correctly, you can send a new master key, but the session keys are generated inside your crypto server.
No, there is no notion of session keys. In fact, remember that you have a satellite and you will inject all the keys for the life, for the complete mission duration. Maybe 1,000 keys. And on ground, you will just deliver key by key to the crypto server. But there is no session key used only for a few minutes.
Mm-hmm. So you're not using the random number generator of the crypto server to generate any kind of secret?
Yes, you use it once to generate the full set of keys. One part will go to the satellite, and the other part will be distributed along the life of the mission. One key at a time. But you have to generate a key once at one moment, unless you use OTAR. If you have OTAR, you can generate new keys.
Understood. Thank you.
In the crypto server, we just use the random generator to make the signature. If for the challenge, we send the random data to the box, and the crypto server has to sign this random data, and to sign, you need a random data. So we also need random data to sign this message, send back to the computer, and check the signature with the public key of this.
Yes, one question. How do you secure the secret, the key, first during injection and then during the operation? Is it secured by, you didn't talk about Tempest or tampering.
No.
Is it linked to the facility that secures you, is secured?
During operations, the key is in the microcontroller's memory. So we rely on the protection of the microcontroller, which has been designed partly for security, which has some features against tampering, which has a DPA-resistant AES engine, but that's all. We do not target very high levels. This is only EAL3+ needed for our missions, so there is no side channel attacks forecasted or things like that. We are not doing classified defense classified data. No.
Hi, thank you for your presentation. I'm not entirely familiar with the space hardware that's available on the crypto hardware acceleration, especially for SDLS. But I do know there's on Earth, like on terrestrial cryptographic networks, you have things like HSMs and those kind of things embedded in computers to have these sort of trusted environments. How does the crypto server relate to those, and what advantages does it offer?
Well, it's part of an ecosystem, complete ecosystem. You have to think the security from the whole system, not only from one point. And the crypto server has been designed to resolve an issue for one final customer saying, I do not want my keys to stay in the control center in a server somewhere, I don't know why. I want a dedicated place, secure, where the key will stay, and I do not want the key to go out of this box. That was the purpose, the main purpose of the crypto server. Voilà. I hope, yeah, okay.
Yeah, one more small question. Maybe I missed it during the presentation. How do you have a mechanism to prevent unauthorized initial setting of the KEK or the later mission keys? So is there an authentication requirement for me to set it in the box?
So for the KE key, as Bruno said, you are the first authentication is the box and the computer close. So this is the first one. Then after we can change the KE key, but the KE key is wrapped and signed, and you have to have the private key to do this. And for the traffic key, they are wrapped with KW, which sign the key and then authenticate the key. So if you send the key not authenticated, the crypto server will reject these keys.
Any other question? No? Well, thank you very much
Okay, thank you.
for this good demonstration.